Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to look at 6.1 in our textbook, 6.1, and this is titled 6.1 in the Linear Algebra book by Gilbert Strang, and this is the introduction to eigenvalues, and eigenvectors. Well, and I think that the best way to start this, to get my special writing tablet glove, the best way to start this is with an example, because otherwise these don't quite make sense. And I found that students struggle to keep in mind what these are, and we lose sight of that over time. So let's work with a matrix we've seen before. This is a matrix, the tridiagonal matrix for the 2x2 version, 2, -1, -1, 2. We use that in another example for the determinant. Today we're going to use it to study eigenvalues and eigenvectors. So let's turn a grid on here. Let's turn a grid on, and we're going to make some graphs. And here's what we're going to do. I'm going to graph three vectors. Let's graph x1 is going to be the vector 0, 1. x2 is going to be the vector of, how about 1? No, you know what? How about 2, 1? Let's try that. Let's try 2, 1. And then let's try, how about x3? x3, let's try this as the vector maybe of 1, 1. And finally, let's try x4 as how about 1, -1? Let's see what happens with these. You know, we could even make x2 one of the columns of A. Maybe we could do an x5. Let's try an x5. We'll see how we feel when we get there. That would be like 2, -1. Or actually, we'll switch them around. How about -1, 2? We'll see what happens with that too. Okay. I think I'm going to need a reasonably big graph here. So I'm going to make some axes. Here's my set of axes. We'll make it about like that and like that. Okay, I'm wondering if that's going to be big enough for us to see. Yeah, I think that's going to be a whole lot better. So let me fix let's fix this line here. Just put that one back in there, and then put that one in. All right, I think we've got what we need. I can always expand this. So here's what we're going to do. We're going to calculate some of these. So let's take the matrix A times the vector x1, and let's see what we get. That's going to be 2 -1, -1, 2, times the vector x1. We said that's 0, 1. Well, notice that gives me the linear combination of none of the first columns, one of the second columns. That's -1, 2. Okay. You know what? Let's try another one too. We'll calculate each one of these. Let's try ax2. Well, that's going to be again 2 -1, -1, 2 times, what did we say? 2, 1. Well, that's going to be 4 -1 is 3, -2 plus 2 is 0. And let's see, A times x3, that's going to be 2 -1, -1, 2, times 1, 1. This is going to be a 2. Let's see, a 2 -1. That's going to be a 1. -1 plus 2 is going to be a 1. And let's see, ax4. I don't want to run out of space here. Let's see, ax4 is 2 -1, -1, 2. Times the vector of 1 -1. All right, let's see what happens here. This is going to be a 2 plus 1 more. That's going to be a 3 minus 1, minus 2, minus 3. And let's see, our last one I wanted to calculate was AX5. So that says 2 minus 1, minus 1, 2 times, let's try this, negative 1, 2. We're just using a column right from the matrix itself. That's going to be minus 2 more, that's minus 4. Then it's going to be a 1. 1 plus 4 is going to be a 5. Okay, now that's a lot of calculating, but it gets us warmed up and ready to go. So let's now graph. We're going to sketch all of these. We'll use different colors. So how about this? So AX1. Well, x1 was the vector 0, 1. So that's this white vector right here. Okay, that is x1. But look at what happens now when I multiply it by a. So a times x1 is the vector negative 1, 2. Well, negative 1, 2 is that vector right there. That is a x1. Okay, let's take another color. How about, I've got this reddish orange color. So now let's graph x2. x2 is over 2 up 1. So that's going to be right there. That is the vector x2. And actually, I'm going to write it just right over here. Oops. That's the vector x2. And then a times x2, though, that was 3, 0. Well, that's right here on the x-axis itself. That is right there. This is a times x2. Okay, let's grab another color. How about this kind of buttercup golden color? How about, so x3 is 1, 1. So let's go, there's x3 right there. That is x3. And now let's graph ax3. Oh, wait a minute. That's the same vector. So x3 is equal to ax3. That's strange. Okay, ax3 is x3. Well, let's try ax4. So x4 is 1 minus 1. We need another color for that. How about this green? So 1 minus 1 is this vector right there. Okay, that is the vector of, what do we say? x4. That's x4. Now, what happens when we multiply x4 times a? So ax4 is 3 minus 3. Well, 3 minus 3, that is way down here. Oh, look at that. It's right on top of, but it's longer than x4. This is ax4. Okay. One more. Let's graph one more. And to do that, we've got this nice blue. x5 is minus 1, 2. Minus 1, 2. Oh, we've already, that was the result of ax1. So we'll just, that's probably not a very good example. Let me change that, because otherwise my graph's going to get too cluttered. So let's just change that. Let's change that. Let's use the other column. How about 2 minus 1? 2 minus 1. So let's fix that down here. Make it 2 minus 1. Okay, so that's going to be a 4 plus 1 more is 6. And it's going to be a minus 2. Minus 2 more is minus 4. Okay, let's graph that. So now 2 minus 1. So 1, 2 minus 1 is this vector right here. That's my x5. There's x5. And then 6 minus 4. 6 minus 4. Holy smokes. 3, 4, 5, 6. 1, 2, 3. It's going to be below my screen, but let's just see what happens when I straighten out the line. Okay, there it is. Now, since it might be cut off, I'm going to write it down here, ax5. Okay, so the question then is why did I graph so many? I have arrows all over. It's two arrows in particular that are of the utmost importance. Notice what happens. Notice that with x1 and then ax1 moved x1. And with x2, ax2 is in a different position than x2. And then let's look again at x5. x5 is in a different place than ax5. But now look at x3 and ax3. They're the exact same vector. And look at x4 and ax4. Well, x4, it didn't change direction, it just changed magnitude. So notice this. So let's come over here and we'll make our important points here. And I'm going to use this white. I think the white stands out best. Notice that a times x1 just gave me some vector. It gave me x1 times 1. And notice that a times x4, this is ax3, I'm sorry. And that a times x4, well, that just gave me 3 times what we started with, x4. So, whoa, what's going on here? This is the key. This is what's happening. So notice this. So the 1 and the 3, these are scalars. These are called scalars. And here's what we say. When how do I want to state that? When ax equals lambda x. So this is in general. I should probably even put that in here. In general, when a times x equals the same x times a scalar, then x is an eigenvector, and lambda is an eigenvalue. Okay, so that's what they do. They preserve the direction of the vector. They might just change it by a scalar. The scalar may be as simple as what we saw here with just a 1, or it might change it by a dramatic magnitude of 3. It could also be a -3, but what it does is it stays on the line of that vector. That is the idea of an eigenvalue and an eigenvector. In our next video, we're going to find out how do you solve those. Hope that helps. Thanks for watching.